Let us discuss the series combination of capacitors. Just like the situation you have studied in your early classes about the series combination of resistances, here also when capacitances are connected one after another like this is called a series combination. Like if these are the capacitors C1, C2 and C3 and the terminals across the combination of three capacitors are A and B. In this situation, this is called as a series combination of the three capacitors. And if we wish to calculate the equivalent capacitance of this combination, we connect a battery across the combination along with a switch. And if we close down the switch, we know well that battery will have a tendency to pull free electrons from the positive side of the plate and place on the other side. So in this situation, this positive terminal is connected to left plate of the capacitor C1. It will pull the free electrons and it will gain a charge plus Q. And same charge will be deposited on the right side of capacitor C3, that is minus Q. And obviously, as on a capacitor, always the charge on the other plate will be equal and opposite to the first plate. Here we can say this plus Q will pull the free electrons from this section or junction of C1 and C2, and a charge minus Q will develop over here. A charge plus Q will develop over here. Similarly, minus Q and plus Q are developed here. So we can say, and here we can see a very important phenomena, that is whenever capacitors are connected in series combination, always the charges on their plates are equal. So we can say, we can also write down a note here for future use, that is in series combination of capacitors, always charges on all capacitors remain equal in a steady state. Actually, it will always be equal, not only in a steady state. If capacitors were initially in charge, you can also write down, if capacitors were initially uncharged. Because if initially there were some charges, it is not necessary that these are equally charged. Now, along with this, we can see the total amount of charge which has been flown through the battery, delta QF, is equals to Q only. So in this situation, if we calculate the equivalent capacitance, then CEQ can be directly written as the amount of charge which is flown through the battery divided by V. V is the potential difference which the battery is maintaining. So now in this situation, if we talk about the potential difference across capacitor C1, this can be written as Q by C1. For the capacitor C2, we can write it Q by C2, and for the capacitor C3, it is Q by C3. Because the charges on capacitors are equal, the potential will be inversely dependent on the capacitances. Now in this situation, we can write the battery potential difference must be equal to the sum of these three potential differences. So here battery potential difference is V1 plus V2 plus V3. Now if we substitute the values here, V can be written as Q by C equivalent. This can be written as Q by C1 plus Q by C2 plus Q by C3. Here Q gets cancelled out and we are getting a relation to calculate the equivalent capacitance of the series combination of capacitors, which is 1 by C equivalent is equals to 1 by C1 plus 1 by C2 plus 1 by C3. And you can also recall that similar relation you have studied for parallel combination of resistances. Whereas in capacitors in series combination, we are using the result of parallel combination of resistances. And in case of parallel combination of capacitors, in the previous section, you have shown that for calculation of equivalent capacitance, we have used the series combination of resistances. There is also a direct hint to remember these two results, so always keep it in mind. Now in continuation for the capacitor combinations, we can write down a note that in series combination, the equivalent capacitance is lesser than the least capacitance of any capacitor used, and in parallel combination the equivalent capacitance is more than the largest capacitance used. This is the reason because once again I am writing the relations. Like for series combination, we have studied that the equivalent capacitance is given by the relation 1 by C equivalent is 1 by C1 plus 1 by C2 and so on for any number of capacitors. And for parallel combination, we can write C equivalent to be equal to C1 plus C2 plus and so on, like in this situation. So here we can state in this situation as we are adding the reciprocals, so C equivalent will be lesser than any capacitor used in the combination, and in parallel combination C equivalent is larger than the highest amount of capacitor used in the combination. So always remember this useful statement. It can be used in many cases also.